JA4 is one of the many solutions used to figure out if a request on the internet is from a bot or a human. This is necessary on the modern internet because bad bots can cause problems if treated like humans. You can spam online forums, you can take down people's web apps, you can try to hack things. Traditionally, we've used simple data on the request or in the packet to work out if traffic seems more like a human or more automated. There's lots of metrics we can use, for example, the IP address or the ASN of the packet. If we look at these values against a database, we might be able to tell if this matches a specific service or a specific country. For example, a single packet might match to an AWS data center in Saudi Arabia. Other methods look at the connection in more detail. Of course, it depends on what the traffic actually is, but if it's HTTP traffic, for example, there'll be headers in the packet. And these headers are typically used to ask the server or tell the server information about the client and what it wants. So for example, if the client wants the website in English or in German or French, there'll be a header for this. There's also a header called user agent. Modern user agent strings are a bit hard to follow. You can see here in the red. What this tells us is that the user is requesting a page that should be suitable and compatible with Windows and with a Chrome browser. It does not mean that this request was sent from a Windows machine running Chrome. It only means that it wants a response that will work with those systems. Again, it's really important to mention that these signals are not proof of anything. In cybersecurity, you might have heard the term non-repudiation. Non-repudiation means a party or a person cannot credibly deny having performed an action because there's cryptographic proof tying that action to them. So if I digitally sign a message with my private key, I can't really claim later that I didn't send it because it's tied to my key. So a user agent has absolutely zero non-repudiation. There is no cryptographic binding between the header and the device that sent it. It's just self-declared metadata, meaning that this information has literally nothing to do with who or what could have actually sent this request. So these are cool signals that might indicate a request is from a bot, right? And there are a lot more signals than user agents. The more attributes of the traffic you look at and you're evaluating, the more interesting signal you get, right? Especially if you use different things to infer other things. Cloudflare does this with its browser identity check. It will look at, for example, the user agent string. If it sees you're on a Windows operating system, but another header suggests you're on Linux, then you might be flagged. So if higher level signals can be spoofed, what if we fingerprint something lower in the stack? And I'm talking about the TCP IP or the OSI layer stack. This is where JA4 comes in. So JA4 is a whole suite of network fingerprinting methods, but we're only going to be looking at the main one, which is to do with the TLS client fingerprint, which is what this lovely diagram shows. So the JA4 algorithm will look at the raw value inside the client hello packet, its TLS capabilities. It will then format these details into a 36-character string divided into 3 sections. So the first 10 sections are not hashed, and they're supposed to be readable. And this is kind of the vibe check of the connection. Is it TCP? Is it quick? Was the request to a domain or was it to an IP? Section B is a hash of all the ciphers the client offered in the handshake, sorted alphabetically. And section C is a hash of the extensions and algorithms offered by the client, also sorted alphabetically. You don't need to remember these things, just important to remember that the JA4 fingerprint is made up of a bunch of details to do with the TLS session. What can we extract from these data points? So quite a lot, but also not that much. Like I said before, you can never be 100% sure with signals like this. If an attacker used, say, 10,000 different IPs, IP-based blocking is useless at that point. However, if all these 10,000 connections have the same JA4 fingerprint, it might be likely this attacker is using the same software to handle the TCP client hello in part of their botnet. But everything will have a JA4 fingerprint, right? So you have to be careful. The same Chrome version or even different versions will probably have the same fingerprint value. But again, Chrome might be establishing a quick connection instead of a TCP, so even the same Chrome version could have two different fingerprints. If the host OS changes, it may or may not change the JA4. VPN usage probably won't, but if there's a proxy in the middle of the connection, this probably will. The main factor that will result in a unique JA4 is if the application has a different code library or runtime doing the TLS handshake. This is good for finding bots because more than likely the attacker has written an application using a standard library or runtime to handle the TLS handshake. And even if it's not standard, it's probably used by the entire botnet. Relying on IPs or ASNs is a very broad approach to bot management, right? Thousands of legitimate users might share a single IP. Modern bots don't even come from data center IPs anymore. Good botnets will use residential proxy networks, they'll hack IoT devices. HTTP headers are application level and therefore slightly easier to modify. TLS handshake behavior is embedded into the networking stack or the library of the application. So JA4 looks at the TLS handshake. So a malicious actor has to recompile their entire networking library or use some sort of specialized tool if we block this, which all in all means this is slightly harder and slightly more effort for the attacker to spoof this signal, which means it's generally a signal that can be trusted more than just an IP. The power of JA4 isn't just that it's harder to spoof, it's valuable because legitimate browsers will cluster into a small number of predictable TLS implementations, and bot frameworks are fragmented across many different TLS libraries and runtimes, creating more variance in their fingerprint.